better with my muscles than I am with my mouth. I work the fairgrounds in the summer or go pick fruit down south. And when I feel them chilly winds, where the weather goes I'll follow. Pack up my traveling things, go with the swallows, and I might get lucky now and then. You win some, I might get lucky now and then.
Chance and probability affect our lives every day. Many things we take for granted depend heavily on probability. We've grown accustomed to the fact that chance influences the world we live in. But how often does one stop to wonder what probability really is?
Honestly.
A bit of thought reveals that this concept, which at first appears simple and intuitive, is in fact very subtle. The mathematical study of probability originated from the analysis of gambling games, most notably using coins and dice in the 17th century. A number of eminent mathematicians, including Pascal, Fermat, Bernoulli, Laplace, and Leibniz, helped develop our understanding of these games of chance and also develop a mathematical theory of probability. Instead of looking at one of many practical applications of the mathematical theory of probability, let us try to find out exactly what a mathematician would call probability. In order to do this, we must come back to the very basics, to the axioms or fundamental rules of probability theory. The first axiom states that for any event E that can potentially occur, the probability P of E that the event will occur is between 0 and 1, where 0 corresponds to an event which can never occur. The certain event, omega, which must always occur, has probability 1. The second axiom states that the probability of at least one of the exclusive events E1 through En is the same as the sum of the individual probabilities of these events. Events are called exclusive if no two of them can both occur. For example, if one flips a coin, then the event heads and the event tails are exclusive, since either one obtains heads or one obtains tails. The second axiom would then mean that the probability of obtaining either heads or tails is the same as the probability of obtaining heads plus the probability of obtaining tails. The third axiom states that the probability of two events both happening is just the probability of the first event times the probability of the second event, given that the first event has occurred. So if, for example, we were to toss two coins, then the probability of getting heads twice is just the probability of getting heads on the first coin times the probability of getting heads on the second coin, given that the first coin has landed on heads. To briefly illustrate how these axioms work, let us look at an example of their application in a simple scenario. Imagine that we roll 2 dice and wish to find the probability of rolling a 3. By the first axiom, this probability will be between 0 and 1. By the second axiom, the probability of getting a 3 is just the sum of the two mutually exclusive events that can lead to rolling a 3, namely the first die landing on a 1 and the second die landing on a 2, and the first die landing on a 2 and the second die landing on a 1. The third axiom then allows us to calculate these two probabilities, using, for example, that the probability of the first die landing on a 1 and the second die landing on a 2 is just the probability of the first die landing on a 1 times the probability of the second die landing on a 2, given that the first die has landed on a 1. Each of these are just 1/6, and therefore we add 1/6 times 1/6 plus 1/6 times 1/6 to get that the probability of rolling a 3 is just 2 divided by 36, which corresponds exactly to the 2 green ticks which we got using the probability tree. These axioms formalize our intuition of calculations of probability and have a vast array of applications. Many theorems follow from these 3 simple axioms, a whole rich mathematical theory. Despite their immense practical utility, a study of these mathematical axioms fails to really elucidate the true nature of the concept of probability. To this day, there are still several distinct interpretations of probability. These interpretations fall into two main classes, which differ upon their explanation of what probability really corresponds to. Epistemological interpretations of probability take probability to be a degree of belief or knowledge of human beings. Objective probabilities, on the other hand, take probability to be a feature of the objective material world, which has nothing at all to do with human knowledge or belief. To give a feel for the difference between epistemological and objective probability, let us consider an example due to Laplace. Suppose that two people, Mr. Blonde and Mr. White, are reliably informed that a coin is biased, but not told the direction of the bias, and are both asked to say what the probability of heads would be. If Mr. White holds an epistemological view of probability, then he will answer that the probability of heads is half, since because of his ignorance of the direction of the bias, there's no reason to prefer one outcome to another. If Mr. Blonde, on the other hand, holds an objective view of probability, then he will answer that the probability of heads is p, where p is between 0 and 1, but all we know about p is that it is not 1/2. This shows in a striking fashion the difference between both approaches to probability. In one case, the probability of heads is half, and in the other, all we know about the probability of heads is that it is not 1/2.
Are you gonna bark all day, little doggy? Or are you gonna bite?
Let us now assume that the probability is an objective feature of the material world. This would mean that the probability of a coin landing on heads is completely independent of our human knowledge about the coin. Perhaps the coin's chance of landing on heads can be more than just a property of the coin itself. It can also depend on a number of other things: the weather, the manner in which it's thrown, the shape of the floor on which it lands, for example. But it does not at all depend on our knowledge about the coin. One way of associating a number with the likelihood of obtaining heads would then be to repeat the throw many times and measure how often the coin might land on heads or on tails. This approach is called the frequency interpretation of probability. For this method to work, we need a sequence of uniform events or processes which differ by certain observable attributes, like heads or tails, for example, in the case of the coin. This is called a collective. The probability of obtaining heads is then the relative frequency of head outcomes to the total number of outcomes. For a perfect coin, for example, we would expect to obtain 500 heads in 1,000 throws, for the frequency of heads to become closer and closer to 1/2 as we increase the number of throws. This definition, however, relies heavily on observation. Moreover, if we really believe there to be a number, called probability, which is intrinsically associated with the chance that an event will occur, then should there not be a way to define probability that does not rely on many repetitions of the same process? The frequency interpretation fails to define the probability of a single event. It says nothing, for example, about the chance that Spain will win the next World Cup. One way of getting around this problem, as was advertised by Karl Popper, is to replace the sequence of repeatable events, the collective of the frequency theory, by a set of generating conditions. These are endowed with a propensity or fundamental disposition to give rise to certain characteristic frequencies, which are equal to the probability of frequency theory, if the experiment is repeated often enough. These generating conditions contain everything which can affect the outcome. The coin toss, for example, they include the shape of the coin, the force of the wind, the way it's thrown, etc. So, to say that the set of generating conditions of a fair coin toss is propensity 1/2, producing outcome heads, means that these conditions, if repeated indefinitely, would produce an outcome sequence in which heads occurs half the time. This propensity interpretation of probability then allows us to associate probabilities to single events. And also, these probabilities obey the mathematical axioms from before if they are defined in this way. Now let us leave behind objective interpretations of probability and ask ourselves what it might mean for probability to be a degree of knowledge or belief. One way of interpreting probability, as was done by Keynes, is as an extension of classical logic. In logic, we can deduce with certainty that a conclusion follows from a premise, or from the assumption that something is true. If our premise is, for example, that all crows are black and Jon Snow is a crow, then it follows with certainty that Jon Snow is black.
Winter's coming.
But suppose now that we have an inductive rather than a deductive case. Say, for example, that we have the evidence that several thousand crows have all been observed and that they are all black. Let us then consider the hypothesis that the next observed crow will be black. Probability, in this way, can be defined as the degree to which the evidence, the thousands of ravens known to be black, partially entails the hypothesis that the next raven will be black. In this logical interpretation, probability allows us to generalize the full entailment of classical logic to various degrees of partial entailment associated with degrees of partial belief. A criticism of this approach could be that there does not seem to be logical relations of probability intrinsically there between pairs of propositions. Is there really a logical relation between thousands of crows being black and the next observed crow's color? A possible resolution would be to adopt the subjective interpretation of probability. In this interpretation, probability is no longer a rational degree of belief, shared by all rational individuals in a hypothesis, given some evidence. Indeed, for subjectivists, different individuals having the same evidence can still have different degrees of belief in a hypothesis.
Wherever you run into it, prejudice always obscures the truth. I don't really know what the truth is. I don't suppose anybody will ever really know. 9 of us now seem to feel that the defendant is innocent. But we're just gambling on probabilities. We may be wrong. We may be trying to let a guilty man go free. I don't know. Nobody really can. But we have a reasonable doubt.
The probability of some event E for a given individual, in this case, is a measure of the rate at which the individual is prepared to bet on E. The axioms of probability we saw before then follow from coherence conditions which make sure that the various degrees of belief fit together. Every day, we are directly affected by probability and chance. But does probability exist in the material world independently of us? Or does it only make sense as a degree of belief held by human beings? Is there even such a thing as the probability that the sun will rise again tomorrow?